Alright, in this video I'm going to be talking about motion graphs. Motion graphs. We've already discussed in this class, if you've been to class so far, we've discussed that there are three different types of graphs. One is a position versus time graph. Position, this can also be distance or displacement. Another type of graph that we said there was is a velocity versus time graph. And the third type of graph is acceleration versus time. I want to focus on this velocity versus time graph in this segment. To start out with that, let's remember position versus time. Let's remember all the things that we've learned about that. So position versus time, the most important thing to remember when you have a position versus time graph, or distance versus time, or displacement versus time, they're all the same graph. The most important thing to remember is that slope represents velocity. Slope represents velocity, and everything you can tell me about the velocity of that graph, everything you can tell me about the slope of that graph, rather, represents the velocity. You can tell me about the velocity. Alright? This graph right here, slope will still represent something, but it will not be velocity, because velocity is what's being graphed on the y-axis here. Okay? So these are the velocity notes that are on my website, and I want to go through these in an effort to talk about a velocity versus time graph. So, on a velocity time graph, slope does represent something. Okay, we're going to talk about what it represents. I want to go back to position time first. When we prove to ourselves that slope represents velocity, here's how we did it. If we calculated slope, we would calculate it by doing rise over run. And in this case, if we did that, the rise is position or distance, and those units would be meters, divided by the run, and the run is time. The x value is time, and those units would be seconds. That comes out to be meters per second, and that is the units that we use to calculate velocity. That's how we prove to ourselves that slope equals velocity in a position time graph. I'm going to use the same line of argument to show you what slope represents on a velocity versus time graph. So, slope is still calculated by using rise over run. Okay? For this graph, the rise, the y value, velocity, this should say meters per second. If we calculated the rise, we would get units of meters per second. That's the units we would get for the rise. And for the run, this is time. Time is in seconds. That's the unit we would get on the bottom. Therefore, the unit we would get if we calculated rise over run is meters per second per second. That might sound familiar to you, because that is actually equal to meters per second times 1 per second, which if you multiply that out, you get meters per second squared. And you might remember that meters per second squared are the units that we use to calculate acceleration. Therefore, we just proved to ourselves that in a velocity versus time graph, the slope represents acceleration. This is the most important thing that you can remember about the velocity versus time graph. That slope represents acceleration. That's the key to analyzing this graph. So if the slope represents acceleration, what that means is that every single thing you can tell me about this slope is also true about the acceleration. Alright? Let's go back to position versus time graphs. In a position time graph, there were three things that the slope could tell me about the velocity. Number one, we could find the actual speed. In other words, the number. If I calculate the actual slope, that would give me the actual speed. The number, the magnitude, in other words, of the speed. I could also find out the direction of the motion. The direction of the motion. What direction the object is moving. And I know that by determining whether the slope is positive or negative. I could also find out whether the velocity is constant or changing. And if velocity was constant, I was looking for a straight line. Straight lines on a velocity time graph would tell me that velocity is constant, whether it's a positively sloped straight line, negatively sloped, or straight across. Constant velocity is a straight line. So slope in a position versus time graph tells me all these things about the velocity. We're going to use this same line of reasoning and talk about 3 things that the slope can tell us about acceleration in a velocity time graph. All right, so the first one, the slope told us the actual speed in velocity on a position time graph. In a velocity time graph, the slope will tell us the magnitude of the acceleration, not the velocity, but the acceleration. Magnitude of the acceleration, in other words, the number. If we calculate the slope of this graph, we get the magnitude of the acceleration in meters per second squared. Okay, so that's almost the same as what the position time graph was, except instead of velocity, we're doing acceleration. Second thing that the slope can tell me is the direction. Just like a position time graph, we could talk about direction depending on whether the slope is negative or positive. But this is not the direction of the motion. This one will tell me the direction of the acceleration. It'll tell me the direction of the acceleration by determining if the slope of the graph is positive or negative. Okay, and remember that the direction of the acceleration will refer to, remember we were talking about, we had our little car, and it depends on whether our rope attached to that car is pulling in a positive direction or the rope is pulling in a negative direction. Okay, that's the direction of the acceleration, what direction the rope is pulling. The last thing that you can tell from the slope is whether or if acceleration is constant or changing. I'll tell you whether acceleration is constant or changing, and just like a position time graph, we can recognize constant acceleration by a straight line. Any straight lines on a velocity time graph tells us that the acceleration is constant. So we can look at this one here. This is constant acceleration. All right, so let's talk about this for a minute. I want you to think about these 2 questions. Pause for a moment if you need to, and let's look at the first question. Look at this graph, and I want you to tell me, how can you tell if this object is moving? All right, hopefully you've had time to think about it if you pause the video. You might have said that, well, we know the object is moving if the graph is sloping upward or downward. And you might think that because you remember with a position versus time graph, we know that this object is moving and this object is moving, but this object is not. Okay? But let's consider this question. I want to draw a line right here that represents another object, and I want you to answer that question. Is this object moving? Pause the video and think about that question and come up with a reason why or why not that object would be moving. All right, you might be tempted to say that no, this object is not moving. But if you said yes, this object was moving, then I would ask you, what's the velocity of the object? Well, we can read, because velocity is what's being graphed, this object has a velocity of 6 meters per second. And if we have a velocity of 6 meters per second, it is not possible to not be moving. So this object is moving. So I'll go back to this question again. How can you tell if the object is moving? You can tell the object is moving if velocity values, which are graphed on the y-axis values, if the velocity is non-zero. Anything other than 0 on the y-axis means that this object is moving. So on this graph here, the only place where this object is not moving is right here when the velocity is 0. It starts from rest and it begins to move. Now, I would ask you another question. Is this object accelerating? The answer is no, because it has a constant speed of 6 meters per second all the way across, never changes. Is this object accelerating? The answer is yes. And if I said, how do you know, I would ask you to refer back to the slope again. If the slope represents acceleration, the slope of this line is 0, and the slope of this line is some positive value. This has a positive slope. If slope is positive, acceleration is positive. Slope is 0, acceleration is 0. Okay, so when we do velocity time graphs, they're going to look like this. There will be positive velocity values here. There will be negative values here. Any y value that is up here in the top or down here in the bottom, in other words, anything that is not right here along the x-axis, that is a moving object, non-zero velocity. Second question, how can you tell if this object is going forward or backward? Pause the video now and think about it. All right, we can tell if this object is going forward or backward based on, well, let's run back to position versus time first. Remember, with position versus time, we can tell if the object is going forward or backward based on the slope of the line. Remember, positive slope told us that it was positive velocity moving forward. Negative slope told us it was negative velocity moving backward. That's not true here. Remember that the positive and negative slope only refers to the direction of the acceleration. It does not refer to the direction of the motion. Remember? So we can have positive acceleration. The rope can be pulling to the right. But if the car is moving to the left, then this car is slowing down. Okay? Or it's actually moving to the left. It still has positive acceleration. The point is, how do we tell if an object is going forward or backward? We tell by deciding if the velocity values, those are graphed on the y, are positive or negative. In other words, if the velocity values are up here, that means the object is moving forward in that part of the graph or in some positive direction. If the velocity values are here, the object is moving backward or some negative direction in that part of the graph. All right, lastly, I would ask you to consider this graph, this velocity time graph, positive values, negative values. Think about this. What is happening in this graph? Pause the video now. Alright, the first thing I want to look at in this graph are the y values. It's very important with velocity time graphs to look at the y values first. Okay, we didn't do that as much with position time graphs, but it's important to do that now. And we look at the y values and we notice that these y values are positive and these y values are negative. And we look up here, if velocity or y values are positive and negative, that's how we tell if the object is going forward or backward. So, this object is moving forward, and this object is moving backward in this case. So, even though this may look like a smooth one-directional motion, it's actually not. And consider, what's the velocity at this point? Well, the velocity here is 0. Which means we've come to a stop here. And if we go forward and come to a stop and then move backward, that means that this object basically, well, that's a negative direction. It went like this. We went forward and then backwards. And let's also notice what's happening to the speed. This entire line is sloped in a negative direction. Negative slope is negative acceleration, which means that the rope is pulling to the left, negative acceleration. So in this case, object is moving to the right, we have a positive velocity, but negative acceleration. When that is the case, we're going to be slowing down. And that's what it shows right here. These velocity values are getting closer to 0. Here we have negative velocities. We still have negative acceleration. When that happens, we must be speeding up, because a negative times a negative is a positive. And that's true because look at these velocity values. They are increasing. they are getting more and more negative, more and farther away from zero. So we move forward and we speed up, or we slow down, and stop, and then immediately begin to move backward and speed up and speed up and speed up. That's what's going on in this graph.